Hey, good morning, everybody. Today we will continue linear regression, and I have ambitious plans to derive the matrix closed form solution for multiple linear regression when we have mm, many features, and also to cover gradient descent. So we'll see how it will goes. How it will go. So last time we had the model y equals w0 plus w1x. And today we will use matrix notation w transposed times x tilde, where my x tilde is x, but extended by a constant 1. So if and the w is the vector of w0 and w1. So if you take the dot product, and the dot product is just the product of coordinates and summation, so w0 times 1 plus w1 times x, you will get our equation. And of course, you can change the order of these vectors and write this as x transposed extended x times w. So I hope you agree with this. So today we will talk about multiple linear regression. That means we can have multiple features instead of just one x. What happened? Instead of just one x, we will have multiple features. And that's why I used this upper index notation, because now I will use lower index for the index of the feature, w1 times x1 plus w2 times x2, and what's good? Let's see. For some reason, trajectory switching. And if we have n features, then we will have n plus 1 term here. Let's see, and let's use maybe d, like dimension x d, and I have forgotten the index of data point x with index I, where index I stands for the item. So we have training data xi and yi, the targets, and I goes from 1 to n, for example, and for each features, vector of features xi, we can represent, well, actually this y should be y hat, but I don't want to use too many notations. Or so in matrix form, it will look like this: w transposed times x tilde, where x tilde now will be um, x tilde will be extended vector by 1, x1, x1, and so on, xd. Oh, and I have again forgotten the superscript I. And yeah, so I think it's much easier to write. You can use also another notation. You can use the dot product notation, like it's the same c dot x tilde I. You can use another dot product notation like this. This is all the same. But I used to just use the vector notation like product of row times column, but these notations are all the same.
You're using the dot product, you don't need the tilde, W tilde. When you're doing the dot product.
Yeah, well, what was the question? What was the question?
So when we're using the dot product, we don't need the W tilde, it's just W.
So the W vector contains the bias term, but X doesn't, we don't have like X0. And that's why we extend our vector X with just a constant 1, because after the dot product, we will get 1 times W0, X1 times W1, and so on. So it's just convenient notation. Okay, and last time we said that we want to minimize the sum of squared errors. So let's write the sum of squared residuals, sorry. So it is the true value minus the prediction, which is W times xi. X1, then the same for x2, and so on. Till point n. And again, I want to use the matrix notation. So I hope you agree that it can be written as follows, as x, y1 minus, instead of prediction, I will use y hat. And actually here, maybe it's also better to use y hat, but, or write y and approximately equal to the linear function. So y1 minus y hat 1, y2 minus y hat 2, the prediction, and so on, times, let's use the new line, times the column, times column, y y1, y2, and so on. So I hope you agree that this sum of squares can be written as the dot product of the vector of differences times itself. Because it will be the first component times first component, the first square, plus second times second, and so on. So if we use if we denote by y all elements of our y's, like y1, y2, and so on, and by y hat all the elements of the predictions, then it can be written as follows. And now let's go back to our weights, to W, and write this more explicitly. So it equals let's see. So what is this y hat? Y hat. So I'm doing this just because the formulas will look much simpler in vector notation than in component-wise. So y hat is the vector of the predictions w times x1 extended, w times x2, and so on. Which can be written in the following form. So I will write now, and then so you will, I hope you will see that it's the same. So we will write the coordinates of the first vector in the first line. So it will be 1, x, 1, component 1, x, 1, the second component, and so on. Oops, x1, second component. Then x1, the third, and so on. And finally, the last component of the first vector. So this is the first line. The second line will, oops, it's also here I should use two. The second line will represent the second extended vector. So I don't like these squares. Let's rid of these. Better. So then second line represent the second data point, and so on. So we will put all the features in rows. This matrix in econometrics is called plan, matrix of plan. So, but For us, it's just the matrix with features in rows. Extended with the first column of ones. And now, if we multiply this matrix by the vector of weights, I hope you will see that this representation is actually true. So let's multiply the first. The first row by the first column. Do you see that you will get exactly the first component, W transpose times X1. I mean, it will be W times 0 plus W1 X1 plus so on WD times XD. So you will get exactly the first component of the prediction. I don't know. Should I write this, or it's clear that the first will be 1 times W0 plus X1 times W1 and so on. The first line will be 1 times W0, X2 times W1 and so on. So, okay, and now we will denote this matrix by X capital. If we denote this matrix by X capital, it will look like this. So instead of writing all these components, all these features, we will just denote this matrix by X capital. So the matrix with features in rows and extended with column of ones. And this will be our prediction. So the sum of squared residuals will be represented now as follows. Instead of y hat, I will use xw. xw. Oops. And we want to minimize that. We want to minimize that. I hope you agree that this notation is looks better than this long sum. And we want to minimize the sum of squared residuals with respect to W, where W now is multi-dimensional vector, not just W0 and W1, but if we have D features, then it's a vector of D plus 1 dimensions. So with respect to W. And you remember how we minimize a function? It's again quadratic function. We take the derivative and solve the equation derivative equals to 0. And we will do this now. So to find the W that delivers minimum of this expression, we should take a derivative but of our sum of squared residuals with respect to vector W. And we will, so what does it mean, a derivative with respect to a vector? It means that we will take a derivative with respect to the W0 first. Then the derivative with respect to W1. But instead of taking the derivatives with respect to each component, we will actually derive now some formulas how to take derivative with respect to the entire vector. And it's called matrix or vector derivatives. And again, you will see that it will make all the formulas much shorter. So by derivative with respect to a vector, we mean the derivative with respect to each component of this vector. The derivative with respect to a matrix, by derivative with respect to a matrix, we would mean the derivative with respect to each component of the matrix. So the derivative with respect to W should have the same size as the W, as our vector W, because we take the derivatives with respect to each component. So now we will instead, so we will substitute the sum of squared residuals by our close, not close, the small notation of dot product. With respect to W, oh, sorry, yep. Instead of SSR, I will write the explicit formula. So we take a derivative from this expression y minus xw transposed times y minus xw. Let's multiply this, open this parenthesis, and we will use this formula. If we have the product of two matrices transposed, it's the same as the first, the second matrix transposed times the first matrix transposed. So my first parenthesis will be y transposed minus, and here I will change the order. It will be W transposed times X transposed times the second brackets. And now we will multiply this parentheses, and we will get y transpose times y minus W. So I will multiply this by y and then this by x. So it will be minus W y transposed times xw. Then I will multiply the second term, this by y and this by xw. So it will be minus W transposed X transposed so times y plus W transposed X transposed times XW. So this then I hope you follow the derivations. So we just multiply this parenthesis. Now I want you to see that these terms actually are equal. And we can use double, like in the square of the sum, a squared plus 2ab, we will get the same formula. Why they are the same? Because here we multiply vector times another vector. But we can use the first vector transposed instead, xw transposed times y. So can you see that it's the same? If we multiply a times b and take a as row, then we can just flip them and use b as row and a as column. But then, if you use this formula, you will get exactly the same term. W transpose X transpose Y. So I can substitute these two terms as just double this term. Okay. I mean, we can use also two terms, but I think it's simple, easier to use just one. Let's see. I will just use 2 in front of this term and erase the third one. Okay, so so this is like analogy of the square square sum, but all our vector, but we have vectors, matrices, but the product of two vectors is just one number. So y transpose times y is just a constant. And yeah, and now we should take the derivative. So the derivative of this first term, can you tell me what will be the derivative of the first term with respect to any component of W vector? It will be zero because it doesn't depend on W. So you can see, you can calculate matrix derivatives. If matrix doesn't depend on W, it will be zero. So the first term will be zero. What will be the derivative of the second term? So I will write it here. If we want to take a derivative of the dot product of vector, let's say, of the product A transposed B with respect to vector B. So if we write this explicitly, A times B will be A1 times B1 plus A2 times B2 and so on. If we take the derivative with respect to the first component B1, we will get A1. If we take the derivative with respect to the second component B2, we will get A2. So as the result, we will get vector A. Can you see that? So again, the derivative with respect to vector. This is calculate the derivative with respect to the first component, to the second. But if we know this formula, we just can apply this formula instead of going through all the math. So the second term here is actually this has this form because we have, so this will be our A and this will be our B. And we take the derivative with respect to B, so we will get A. But this actually A transposed So we can rewrite this as X transposed Y and everything transposed. So this will be our A transposed. So if you apply transposition, you will get Y transpose times X. So this is our A transpose, and the derivative will be just A. So it will be, so the derivative of the first term is 0. The derivative of the second term will be negative X transposed Y. So do you have any questions about the second term? So we just used this form. So for the last term, it's called quadratic form because here W is kind of squared. I don't want to derive the formula. I will just use the ready formula from Wikipedia. But if you want, you can derive it exactly the same as I derived for the dot product of two vectors. So you can Google, for example, matrix calculus, matrix calculator, calculus, and find all these formulas here. Okay. So let's see. Yeah, for example, the first one, A times X with respect to X, and here two ways. One returns the second column returns the shape of X. The first column returns the shape of X transposed. So we want to use the second column. And okay, here's the line for matrix derivative. So it will be matrix plus matrix transposed times X. And we will just use this formula. But in our case, our matrix is symmetric and A transposed are the same. So we will just get 2A times X. It's the same as we take derivative of X squared. It's just 2. So let's go back to our derivations. So every time when you multiply matrix by transposed, the result will be symmetric. So that's why this matrix and the transpose of this matrix, the transpose of this matrix will be, the second will be first transposed, the first will be second transposed, but it will be exactly the same, X transposed X. So from that formula, from Wikipedia, it's 2A, in our case, 2X transposed X times W. And now we equate this to 0 and solve with respect to W. And we will get closed form solution. So are you okay with this final result? Even though, yeah, we just use the formula from Wikipedia, but we hope that the formula in Wikipedia is correct. So, but yeah, if you want, you can double check it. Let's solve it now with respect to W, and this will be actually our solution. So divide by 2, and we will get X transposed X times W equals X transposed Y. Now, if you remember a little bit the algebra, if we want to rid of this matrix, we should multiply by inverse matrix from from the left. And matrix by inverse will give us just identity, and identity times any vector will be just itself. So final answer is that W is the inverse of X transposed X times X transposed Y. Okay, voila. You remember last class we spent maybe more than half of class just to find the formulas for linear regression with one feature. Now, in half an hour, we derived the formula for arbitrary number of components, where X is the matrix with our features in lines and extended by one. Okay, now we can code this. So in your third homework, I ask you to implement linear regression in 3 ways. Yep.
I think by the previous expression, we can simply the inverse of x times y, because you have two transposes at the front. You can multiply both. You can put up x transpose, the inverse of the x transpose on both expressions, and just use inverse there.
What is it?
Get rid of and use an inverse matrix on the right side, on the left side to get rid of.
Oh, okay. The question was what? The question was what if we multiply here by X? Typically, X transposed inverse is denoted by X negative transpose, but it's the same as X transposed and -1. So if we multiply our equation here by this inverse transpose, then maybe this will be identity, this will be identity, and we will get just y equals double x double. The answer is that our matrix X is not squared. It has the shape of the number of features, d plus 1. So this is the number of columns, and the number of rows is m, the number of points. And if the matrix is not squared, we can't inverse that matrix. So if it would squared, we could inverse, but it's not. Oh, and actually, I've never thought about this, but now it just came into my mind. What if this matrix were squared? It means that the number of unknowns, the number of features is exactly the same as the number of points. So it means that we have the number of equations the same as the number of unknowns, and then there's just unique solution. And then we could get this unique solution. W equals, but unfortunately, typically we don't have this. Well, actually, but wait a second. But here we also can get unique solution if we have inverse matrix. Well, anyway, so we can do this because X is not squared. So the inverse just undefined. But yep, so okay. Now you don't need to code with me, but you will need to do this in your homework. So in your homework, homework 3, I want to implement, I have to implement the, yeah, so I tried here to write like in coordinate notation that we have done, but we will use just the matrix notation. So I ask you to implement this class, and the first way to calculate the linear regression will be matrix. The second will be gradient descent and the last one will be stochastic gradient descent. So today we will, let's start coding this matrix linear regression, but I will use another notebook. Okay, so I will use the data set with from Galton's notebook with heights of children and parents. So as features, I will use the average height of the parents, and as the targets, the height of the children. Split into train test. Bless you. And in the first line, I'm using just built-in linear regression. Built-in linear regression will return you these parameters, W0 and which is called intercept, and coefs will return the remaining components of W. And you can find the score. And if you visualize this, it will look like that. So what I'm doing here, I just, my y, I take x, and my y is just this linear function, w1 plus w0 plus w1 times x. Okay, now we will write our implementation. There are many parameters. For now, we will use linear regression without regularization. We will talk about regularization next week. And to make this similar to built-in function, we will use these attributes intercept, which is W0, and other coefficients in coefs. So they're initialized by nonce, and when we fit our data, we will just memorize our, we will just create our matrix X. So what I'm doing here, if it's pandas, I cast into NumPy array and add the column of ones to make the extended matrix. If it's a NumPy array, I just add the column of ones. And also target, if it's pandas, I cast into NumPy array. Okay, our first function, weights. Let's, well, actually it provides the correct code. Okay, well, I will just press tab. So if you look at our derivations, our formula looks like this. W is the inverse matrix of of X transpose X, and let's see if, let's just analyze the code that was suggested by AI assistant. So what is going on here? So the X transposed is multiplied by X, then inverse. So this is inverse. So this part is this part, the inverse of X. So for matrix multiplication, you could use this at, like just use X transposed. But you could also use dot. So if it's more clear for you, let's see, you could use also just at here, and then take inverse matrix. Then we multiply this inverse by X transposed again. You could use at instead. Maybe it's more clear. But dot, and then we multiply everything by y. And it's better to use dot product here because vector y has dimensions n, comma, and that's it. So it's kind of, it's not a matrix. And the dot operation will actually take the dot product. It's more safe. Otherwise, maybe we should reshape our y to make this n by 1, and then we could use this at to multiply. But if it's if you don't want to add extra dimension, you can use dot product. Okay, and we're done actually. And after we calculated this w, we assign to intercept the first component and to the vector of coefficients the rest. Let's see what is the shape of this. Actually, I asked to return the shape two-dimensional. So to get two-dimensional, we can just do reshape. Reshape. I add one column. Then it will be d times 1 instead of just d comma. Okay, and I will go to prediction now. Predict. So predict. Oh, by the way, we didn't use regularization, so here we should do if regularization self-regularization is none. I just prepare for the full code. Then we will do this. Oops. Okay. And then will be else, and then you will write the code with regularization. So prediction, for prediction, as you remember, our W, our prediction Y was just X times W. And for prediction, we can use arbitrary matrix X. And I wrote the code to cast to NumPy and add the column of ones. So we can use just or X dot product XW or X dot W. So yeah, that's it. And let's see, maybe it will work now. Just run it. And create object of regression. Without any parameters for now. Then we will fit. And after fit, actually, you can find the score is not implemented for now. You can find the prediction y pred equals to regression predict on y on x test. Okay, y test predict w. Oh, okay. I'm sorry. In our prediction, the w is not defined, so we should write define w as follows: intercept and other coefficients. So just because attributes of my class are separate, bias and other features. So I should create my W from these attributes again. And squeeze will remove the extra dimensions, so W will be one-dimensional. Okay, now it should work. And when we calculated the prediction, we can, for example, calculate the score on y. So first of all, I want to see the shape of my prediction shape. Okay, it's one-dimensional. So we can calculate the MSE, for example, or R-squared score from mean squared error or R-squared, and I can calculate R-squared between y-test and y-test predict. And if you compare this number with the number that we saw when we used built-in function, it's exactly the same. You remember we started with built-in function, and now it's we wrote our function, and the score is the same. So I have this actually function here, r squared. I think you can write it yourself. Okay, so now do you understand what we have done? We just wrote the function for weights. Where was it? Here, for weights that we derived on the whiteboard. And I hope you appreciate now this matrix notation, because we don't use for loops. We don't calculate the derivative with respect to every w. We just use matrix notation. The only problem that you may encounter is when the matrix is not invertible. And it will happen when you will have dependent features. That's why you remember we removed the first column from one hot encoder. If you don't remove, you will get determinant 0 and it's not invertible. Okay, now let's go to numerical solution, which is called, because none of the packages use this closed form solution for linear regression. All packages are using actually numerical solution, gradient descent. So let's go to gradient descent. Hopefully we have time. And the idea of the numerical solution is as follows. So our next topic is gradient descent, or GD. And then we will talk about stochastic gradient descent. It will be SGD. So this derivative with respect to vector W from our function, let's say f, but it was the sum of squared residuals. In math, has usually notation of gradient nabla of gradient of f with respect to W. So, and so this is, as you remember, this is the vector of partial derivatives. The vector of the derivatives with respect to each component. So this is another notation, and it's called gradient with respect to W. So that's why it's called gradient. Now let's see how it works. Assume we have a function y equals x squared. Parabola. And in all numerical methods, we start with some approximation to the minimum, and then we begin iterative process. So let's start from, for example, I will a little bit abuse my notation. Now I will use index for the time step. So, but it's one-dimensional. So let's start with first point x0, for example, 2. What will be the value of y at this point? It will be 4. So we calculate the y at this. Well, my drawing is not in scale, but it's okay. So it will be 4. And after that, do you remember we calculated the vector perpendicular to our line, and we looked at this vector, and this vector actually will be the derivative. So let's calculate the derivative. Derivative is 2x. So derivative at this point will be 4. Derivative at this point will be 2 times 2. So, and you can see that it actually points in the positive direction. So how to choose the second point, x1, next point? Just using the derivative. We should go in which direction to find the minimum? To the right or to the left? To the left. So we should update our point using negative derivative. Does it make sense? So next point we will calculate as previous point, but using anti-gradient minus derivative. For now, I'm using derivative. Later on, when we will have multidimensional case, we will use this notation, now gradient. So just minus, subtract the derivative at our previous point. Unfortunately, if we calculate this, it will be, oh, maybe not, maybe it will be okay. So it will be 2 minus 4. Oh no, it will be negative 2. So our new point will be here, x1. And if you calculate the derivative at this point, it will be exactly the same, but with opposite sign. And you will just juggle between these 2 points infinitely. How to update this procedure, actually, to make our algorithm convergent to the origin. Yes?
Method?
Well, Newton's, now we talk about gradient descent, which uses first derivative. Newton's method uses second derivative. But I mean, just to a little bit change this formula to reduce this step. So we should add here a constant smaller than 1. And then we will get the next point a little bit closer to 0. And this is called gradient descent method. So we add here coefficient. This coefficient is called learning rate. So eta is between 0 and 1. So it will help us not overshoot too much. And that's it. So this is the algorithm. So if you use, for example, eta 1/2, your new point will be at point 1. Or maybe not 1, but it's a 2. Oh, no. If we use eta 1/2, what will be the new point? If I multiply 4 by 1/2, it will be 0. So we will converge in one step. Okay, so I hope you get the idea of this method. But if it's not 1/2, still you will get somewhere here, then a little bit closer because your eta is smaller than 1, and you will converge to 0. So let's implement this in our code. Hopefully, we have actually the expression for derivative. Let's a little bit just simplify it. So it's 2. We can factor out x transpose just, and then it will be x w minus y. So we just should, yeah, we can use this formula in our code. So now we will go to method of calculation GD, gradient descent. And the step of iteration is called epoch. So here is for epoch. Again, we don't use regularization. So if regularization is none, okay, and it looks like it provided the correct code. So let's see. So if learning rate is none. Aha. Well, learning rate is not self now, so it's correct. So learning rate is just LR, but something is missing here. So if we look at our formula for gradient, here it is. And this generated formula, so it looks almost the same. So x transposed times xw minus y, but 2 is missing. 2 is missing. And also, but well, it's just a constant. If our learning rate is our learning rate is typically smaller than 1/2. So then if we multiply by 2, it's not a big difference. And also, if we use loss function, then we should divide by n. So I would also divide by the length of points. Okay, so it's early to change to do these coefficients. Wait a second. So we update our weights by this formula. X minus, in this case, W minus learning rate times the gradient of our function. And in the end, after these iterations, this is a parameter that you can set up the number of iterations, max iter. We should return self coef and self intercept. Okay, and we're done. Now we can test our function. Method will be now what is it called? Weight calc. Weight calc will be gradient descent. There is a question. Where did you put the last return statement? The last return statement will be the same for all methods. Where is it? Oh, for here we don't need the return statement. Here we just store the weights in our parameters self-coefs and self-intercept. So, and we use them then in prediction. Weight calc is gradient descent. Let's fit. Oh, and here actually we can see the something weird. So this is our prediction, this is our data, but we run into nonce. It means that our method diverges. It means that or learning rate is too large, or our features are too large. If we scale our features, yeah, I think we have 5 more minutes. So let's scale our features. So I will add just one line. So for this gradient descent, I wrote for you this visualization. Let's apply scalar import now from escalon what's called feature no transforms. Second. Oh, it's pre-processing. It's called pre-processing. Import standard scalar, and then if we apply scalar to our xtrain, so let's create the object scalar, standard scalar, and fit on x train. And apply scalar dot what's called transform, and try now. Well, oh, you can see that it looks like it converges. So this root mean squared error goes down. So, but it goes a little bit slow. But you can see that our line actually goes closer to the points. So, if we would use the larger number of epochs, then it would fit better. For example, learning rate by default is -3. Let's try -2. So with higher learning rate, it converges faster. Does it make sense? Because okay, so I'm glad that we covered at least the main machine learning algorithm, gradient descent. All neural networks they trained with gradient descent. So, and just to give you an idea why for unscaled and scaled data, the performance is different. For unscaled data, your function, the sum of squared errors, if your features are large, your function values also will be large. And when you calculate gradient, the gradient also will be large. So you're most likely to overshoot the minimum. If you scale your data, your function takes smaller values. When you take gradient, the gradient also will have smaller values, and it will help for the convergence. Okay, I think we will need one more lecture, and maybe yeah, I will change the due date for homework 3 because we will need to cover stochastic gradient descent. Then we should cover feature selection, and then you will be ready for homework 3. But you can start working on the first part. Okay. Yeah. Let's. Oh, I changed the learning rate in the initialization of my class. Yes, this recording I will upload right now on my actually all the recordings are on GitHub.